Before we explore this extraordinary story, if you appreciate detailed historical accounts that reveal the hidden technological battles behind World War II, please subscribe to our channel and hit the notification bell so you never miss our comprehensive documentaries. In the desperate skies over Germany during 1944, Luftwaffe commanders watched with growing horror as American bombers and fighters seemed increasingly immune to anti-aircraft fire that had previously been effective. German flak batteries fired thousands of shells at bomber formations, calculating precise altitude settings and timing fuses for airburst detonations at predicted locations, yet hit rates declined mysteriously while ammunition consumption soared. German fighter pilots reported that Allied aircraft seemed surrounded by protective barriers that destroyed German planes approaching too closely, yet no visible weaponry could explain these losses. The mystery deepened until December 1944, when German forces overran American positions during the Battle of the Bulge and captured intact artillery shells equipped with devices the Americans called VT fuses. When German engineers at the Kummersdorf Proving Grounds finally examined these revolutionary proximity fuses, they discovered technology so sophisticated and manufacturing so precise that it forced a complete reassessment of what was possible in weapons development. This is the story of how German scientists dissected the captured VT fuses, how they came to understand that these devices created 140-foot airburst kill zones that made anti-aircraft fire devastatingly effective without requiring precise range calculations, and how this single technological breakthrough revealed an industrial and scientific capability gap so vast that even Germany's most advanced laboratories could not hope to bridge it during wartime conditions. Before we explore this extraordinary story, if you appreciate detailed historical accounts that reveal the hidden technological battles behind World War II, please subscribe to our channel and hit the notification bell so you never miss our comprehensive documentaries. The cold January morning of 1945 found Dr. Herbert Wagner standing in the heavily secured examination facility at the Kummersdorf artillery range south of Berlin, staring at a device that would shatter his understanding of what American science and industry had achieved. Before him on the examination table lay several artillery shells captured during the recent Ardennes offensive, and attached to their noses were cylindrical devices approximately 5 inches long and 3 inches in diameter that German intelligence had been desperately trying to obtain for over a year. These were American VT fuses, the proximity fuses that had revolutionized anti-aircraft warfare and had contributed significantly to the dramatic decline in German aircraft losses inflicted by Allied flak. Wagner, a brilliant scientist who had developed Germany's rocket-powered anti-aircraft missiles and who understood explosives and fire control systems as well as anyone in the Reich, had been summoned urgently from his work on advanced weapons to lead the examination of these captured fuses. The High Command wanted answers about how these devices worked, whether Germany could produce similar weapons, and most critically, whether any countermeasures could be developed against technology that was decimating German air operations. The variable time fuse, which the Americans euphemistically called the VT fuse to disguise its true nature as a proximity fuse, represented one of the most closely guarded secrets of the Allied war effort. Development had begun in 1940 when British scientists recognized that conventional anti-aircraft fire was woefully ineffective. Traditional anti-aircraft shells used mechanical time fuses that had to be set before firing based on calculations of target altitude, speed, and trajectory. Gunners observed approaching aircraft through optical rangefinders, calculated the time required for a shell to reach the predicted interception point, set the fuse accordingly, and fired. If the calculations were correct and the aircraft maintained course and speed, the shell would detonate near the target and the expanding shrapnel cloud might damage or destroy the aircraft. But aircraft rarely maintained constant altitude and speed when under fire, and the calculations required were complex and time-sensitive. Hit rates with time-fused anti-aircraft shells averaged approximately 1 hit per several thousand rounds fired, meaning that destroying a single aircraft typically required expending enormous quantities of ammunition. The proximity fuse concept promised to revolutionize this dismal equation. Instead of relying on precise time settings that would detonate the shell at a predicted location whether or not the target was actually there, a proximity fuse would sense the target's presence and detonate automatically when the shell passed closest to the aircraft. This eliminated the need for precise range calculations and timing, dramatically improving hit probability. A shell equipped with a proximity fuse simply needed to pass within a certain distance of the target, and the fuse would automatically detonate at the optimal moment to maximize damage. The theoretical advantages were obvious, but implementing the concept required solving extraordinarily difficult technical challenges. The fuse needed to contain a miniaturized radio transmitter and receiver that could detect targets withstand the tremendous acceleration forces of being fired from a gun, operate reliably under extreme conditions, remain safe until fired, and cost little enough to be used on disposable artillery shells rather than being limited to expensive guided missiles. American scientists, primarily working under the National Defense Research Committee and later the Office of Scientific Research and Development, had achieved what many thought impossible. They had developed a proximity fuse that contained a complete miniaturized radio system including transmitter, receiver, amplifier, and detonation circuit, all packaged into a device small enough to replace the standard mechanical fuse on a 5-inch anti-aircraft shell. The fuse operated on a simple but elegant principle. A small radio transmitter broadcast continuous radio waves from the shell as it flew toward the target. When the shell approached within range of the target aircraft, the radio waves reflected off the aircraft's metal structure and returned to the fuse's receiver. The received signal was amplified and compared to the transmitted signal, and when the received signal reached sufficient strength indicating close proximity to a metal object, the detonation circuit fired the shell. The entire process occurred in fractions of a second as the shell passed near the target, detonating at the optimal distance to create a lethal shrapnel pattern. Dr. Wagner had read intelligence reports about proximity fuses and had understood theoretically how they might work, but he had never imagined the Americans could actually build such devices in quantity for battlefield use. The technical challenges seemed insurmountable, particularly the requirement to package sophisticated radio equipment into a small rugged package that could survive the shock of being fired from a gun. Anti-aircraft guns subjected shells to accelerations exceeding 20,000 times the force of gravity for brief periods during firing. No vacuum tube radio equipment Wagner knew of could survive such forces. The glass tubes would shatter instantly and the delicate internal components would be destroyed. Yet American intelligence consistently reported that proximity-fused anti-aircraft shells were being fired in vast quantities and were achieving hit rates far exceeding conventional time-fused shells. German aircraft losses to anti-aircraft fire had increased dramatically during 1944, and pilot reports described shells that seemed to explode at precisely the right moment, even when aircraft were taking evasive action that should have made conventional flak ineffective. Wagner's examination began with external inspection of the intact fuse, and even this preliminary assessment revealed manufacturing sophistication that impressed and disturbed him. The fuse body was precision, machined aluminum with surface finish quality that indicated advanced manufacturing processes and rigorous quality control. Every component visible from the exterior was precisely made and carefully assembled. The threaded fitting that attached the fuse to the shell was machined to tolerances that would ensure reliable installation under combat conditions. Safety mechanisms visible through inspection ports appeared robust and well-designed. The overall impression was of manufacturing excellence that reflected unlimited resources and sophisticated production methods. Wagner compared this mentally to German fuse manufacturing, which increasingly suffered from material shortages, quality control problems, and the use of forced labor that lacked the skills necessary for precision work. The external appearance of the American fuse suggested that it was the product of an industrial system, operating at peak efficiency without the resource constraints and workforce limitations that plagued German production. The critical phase of the examination began when Wagner's team carefully disassembled one of the captured fuses to examine its internal components. What they discovered left the experienced German scientists stunned and frankly demoralized. The fuse contained a complete miniaturized radio system built around vacuum tubes that had been specially designed to withstand gun launch forces. The tubes themselves were engineering marvels, tiny devices with rugged internal construction that used heavy wire elements and mechanical design, features that allowed them to survive accelerations that would instantly destroy conventional radio tubes. Wagner had never seen vacuum tubes like these, and knew immediately that they represented years of development and sophisticated manufacturing capabilities. The tubes were manufactured with precision that exceeded anything in German production, with carefully controlled internal geometries, special materials, and assembly techniques that produced devices both tiny and rugged. The radio circuit design revealed electrical engineering sophistication that Wagner found remarkable. The circuit used a superheterodyne receiver design that amplified the weak reflected signals and compared them to the transmitted signal to detect targets. The components were miniaturized beyond anything Wagner had seen, with resistors, capacitors, and transformers manufactured to tiny dimensions while maintaining reliable performance. Every component was mounted on a rigid chassis designed to distribute launch forces throughout the structure rather than allowing them to concentrate on individual components. The chassis itself was a precision casting with mounting points positioned precisely to hold components securely. The wiring was neat and systematic, showing evidence of assembly by skilled workers following carefully designed procedures. The detonation circuit included safety mechanisms that prevented premature detonation and armed the fuse only after the shell had traveled a safe distance from the gun. Wagner's team conducted careful measurements and tests on the fuse components, documenting specifications and attempting to understand design choices. They discovered that the radio operated at approximately 180 to 220 MHz, a frequency range that provided good target detection while allowing the antenna to be small enough to fit within the fuse body. The antenna was a small rod that extended from the fuse nose, designed to radiate and receive radio signals efficiently despite its compact size. The power supply was a small battery activated by the launch forces, providing electrical power for the few seconds the fuse needed to operate. The battery technology was sophisticated, using materials and construction methods that provided high power output in compact packages. Every aspect of the fuse's design reflected careful optimization, balancing multiple competing requirements including size, weight, ruggedness, performance, reliability, cost, and safety. The examination revealed the kill zone characteristics that made the proximity fuse so devastatingly effective. The fuse would detonate the shell when it passed within approximately 70 feet of a target aircraft, creating a shrapnel pattern that was lethal within a sphere of approximately 140 feet in diameter. This meant that any aircraft within that 140-foot kill zone would be subjected to high-velocity steel fragments that could penetrate aircraft structures, destroy engines, kill crew members, and cause catastrophic damage. Traditional time-fused anti-aircraft shells created similar shrapnel patterns, but only if they detonated at the right moment, which required precise range calculations and cooperative targets. The proximity fuse ensured detonation at the optimal moment automatically, eliminating calculation errors and accounting for target evasion. Wagner calculated that the proximity fuse probably improved anti-aircraft effectiveness by a factor of 5 to 10 times compared to time fuses, meaning that one proximity fused shell had the same hit probability as 5 to 10 conventional shells. The implications were staggering and deeply disturbing for German air operations. If American anti-aircraft fire was 5 to 10 times more effective per shell fired, then German aircraft faced vastly increased danger from flak that was already a significant threat. German bomber and fighter pilots would find it increasingly difficult to survive missions that required flying through anti-aircraft fire, and the attrition rates would climb accordingly. More broadly, the proximity fuse represented a technological achievement that Germany could not match with available resources and industrial capacity. Wagner recognized immediately that even if Germany understood how the fuse worked in principle, actually manufacturing such devices in quantity would be impossible under current conditions. The specialized vacuum tubes, miniaturized components, precision manufacturing, and quality control required were all beyond German capabilities in 1945. Dr. Wagner compiled a detailed technical report documenting his team's findings and assessing German prospects for developing comparable technology. His report was brutally honest about the sophistication of American engineering and the impossibility of German replication. He noted that the proximity fuse represented integrated development across multiple technical disciplines, including radio engineering, vacuum tube technology, miniaturization techniques, rugged design for high-G environments, explosives and detonation circuits, power supplies, and manufacturing processes for precision assembly. Each of these disciplines required specialized knowledge and industrial capability, and the Americans had successfully integrated all of them into a device that could be manufactured in quantity at reasonable cost. Wagner estimated that developing German proximity fuses from scratch would require at least 2 to 3 years of intensive development, even if resources were available, and that manufacturing capability would require building entirely new production facilities with specialized equipment and highly trained workers. The report noted that Germany had actually attempted proximity fuse development earlier in the war but had abandoned the effort due to insurmountable technical difficulties. German scientists had understood the theoretical principles but had failed to solve the practical implementation problems, particularly the challenge of building vacuum tube radio equipment rugged enough to survive gun launch. The Germans had focused instead on acoustic fuses that would detonate shells based on detecting engine noise, but these had proven unreliable and ineffective. The American achievement in building practical radio proximity fuses represented a quantum leap beyond anything Germany had accomplished or could hope to accomplish in the remaining war period. Wagner's report concluded that Germany had no realistic prospect of developing countermeasures beyond tactical adaptations, like flying lower to reduce flak exposure or using radar jamming that might interfere with proximity fuse operation. Though this latter approach remained theoretical as no one knew whether the fuses were susceptible to jamming. The captured fuses were shared with other German research facilities for additional analysis, and each examination reached similar conclusions about American technological sophistication and German inability to replicate it. Scientists at the Telefunken Laboratories, Germany's leading electronics manufacturer, examined the miniature vacuum tubes and confirmed that they represented manufacturing capabilities beyond anything German industry could achieve. The tubes required specialized machinery for manufacture, extreme precision in assembly, rigorous testing and quality control, and materials that were increasingly scarce in Germany. Telefunken engineers estimated that even if they understood exactly how to manufacture the tubes, building production facilities and training workers would take many months and would require resources that Germany simply did not have. The psychological impact of the proximity fuse examination on German scientists and military officers was profound and contributed to the growing realization that Germany was losing the technology race across multiple domains. The proximity fuse joined a lengthening list of Allied technological achievements that Germany could not match, including advanced radar systems, reliable long-range bombers, powerful aircraft engines, sophisticated computing devices for fire control, and industrial processes that enabled mass production of complex equipment. Each examination of captured Allied equipment revealed the same pattern: sophisticated design, precision manufacturing, high-quality materials, and industrial capacity that exceeded German capabilities by widening margins. The proximity fuse was particularly demoralizing because it was not a prototype or experimental device but a production weapon being manufactured by the hundreds of thousands and expended freely in combat as disposable ammunition. The tactical and operational impact of American proximity fuses had been devastating for German air operations throughout 1944 and early 1945. Allied naval vessels equipped with proximity-fused anti-aircraft shells achieved dramatically improved effectiveness against German aircraft, particularly against the guided glide bombs that Germany had developed as standoff weapons for attacking ships. German pilots attacking Allied vessels with Fritz X or HS-293 guided bombs found that the intensive anti-aircraft fire they encountered was far more accurate and deadly than earlier in the war. Proximity-fused shells would detonate near the slow-moving glide bombs or the attacking aircraft, destroying them before attacks could be completed. The effectiveness of Germany's guided bomb attacks declined precipitously once proximity fuses were deployed, forcing Germany to abandon tactics that had previously been successful. American ground forces began using proximity-fused artillery shells in Europe during the Battle of the Bulge in December 1944, and the results were catastrophic for German troops. Traditional artillery fire required shells to burst on impact with the ground or obstacles, limiting their effectiveness against troops in trenches or behind cover. Artillery shells equipped with proximity fuses would detonate automatically at optimal height above the ground, typically 15 to 30 feet, creating an airborne explosion that rained shrapnel downward into trenches and foxholes that would have provided protection against ground bursts. The 140-foot kill zone of each proximity fuse shell meant that German troops had no effective cover against American artillery once proximity fuses were deployed. Casualty rates from American artillery fire increased dramatically, and German soldiers reported that the airbursts seemed uncannily timed and that no position provided adequate protection. German forces captured enough proximity-fused shells during the Bulge offensive to provide multiple specimens for examination, but they also captured them too late in the war for the knowledge to have any practical application. By January 1945, Germany's military situation was deteriorating rapidly, with Allied forces advancing from both east and west, industrial production collapsing under strategic bombing, and resources depleted to the point where even basic military operations were becoming difficult to sustain. Knowledge about how proximity fuses worked provided no benefit when Germany lacked the capacity to develop similar weapons or effective countermeasures. The examinations documented German technological inferiority but changed nothing about the war's trajectory or outcome. Dr. Wagner and his colleagues attempted to develop some tactical countermeasures based on their understanding of proximity fuse operation. They recognized that the fuses operated by detecting radio wave reflections from metal targets, which suggested that reducing an aircraft's radar cross-section might make it harder for fuses to detect. They recommended that German aircraft incorporate radar-absorbing materials or coatings that would reduce reflections, essentially pioneering the concept that would eventually become stealth technology. But implementing such measures required materials and manufacturing capabilities that Germany lacked, and the recommendations remained theoretical. They also suggested that formation flying might be avoided to prevent proximity fuses from detecting multiple aircraft. But this recommendation contradicted tactical necessity for defensive formations and was generally ignored. The scientists investigated whether radio jamming might interfere with proximity fuse operation, reasoning that if the fuses operated on radio frequencies, then powerful transmitters might be able to jam or confuse them. However, they lacked detailed knowledge about the fuse frequencies and signal processing methods, and developing effective jamming required radio equipment that was increasingly scarce as Germany's electronics industry struggled with material shortages and bombing damage to factories. Some experimental jamming equipment was built and tested, but results were inconclusive, and the program was abandoned as the military situation collapsed completely in the final months of the war. The examination of captured proximity fuses revealed not just the sophistication of the devices themselves, but also the comprehensive American approach to weapons development that integrated research, development, testing, manufacturing, and deployment. The scientists examining the fuses recognized that creating such weapons required far more than brilliant individual scientists or engineers. It required systematic organization of research programs, generous funding that allowed extensive testing and iterative refinement, sophisticated manufacturing facilities with skilled workforces, rigorous quality control that ensured reliability, and logistics systems that could distribute hundreds of thousands of fuses to military units operating globally. The Americans had built an entire industrial and organizational ecosystem supporting weapons development, and that ecosystem was as much a weapon of war as any individual device it produced. German weapons development, by contrast, had become increasingly chaotic and uncoordinated as the war progressed. Multiple organizations pursued competing programs, resources were spread across to many projects with insufficient support for any to achieve excellence. Manufacturing capacity was insufficient and increasingly disrupted by bombing. Quality control deteriorated as skilled workers were drafted or killed, and logistics became progressively more difficult as transportation infrastructure was destroyed. The proximity fuse examination made these systematic failures painfully obvious, illustrating how American organizational and industrial strengths had created decisive advantages that German technical brilliance could not overcome. One particularly galling aspect of the proximity fuse examination was recognizing how long the Americans had been developing and deploying these weapons while German intelligence had failed to appreciate their significance. Evidence suggested that proximity fuses had been in operational use since at least mid-1943, deployed first in naval applications and later in ground artillery. This meant the Americans had been manufacturing and expending hundreds of thousands of sophisticated radio devices while Germany remained largely ignorant of their existence. The intelligence failure compounded the technological failure, reflecting broader problems in German military and scientific organizations that failed to identify and respond to Allied technological developments until too late to matter. Dr. Wagner's team attempted to estimate American proximity fuse production volumes based on reports of their usage, and the calculations were staggering. The Americans appeared to be producing proximity fuses at rates exceeding hundreds of thousands per month. Treating these sophisticated radio devices as expendable ammunition, Wagner knew that German electronics production could not approach such volumes even for conventional radio equipment, much less for miniaturized, ruggedized devices like proximity fuses. The production volume alone demonstrated industrial capacity that dwarfed Germany's capabilities, reflecting advantages in factory capacity, skilled labor, material supply, and manufacturing technology that accumulated into overwhelming superiority. The miniaturization techniques evident in the proximity fuse impressed German scientists and suggested advances in electronics manufacturing that went far beyond weapons applications. The Germans recognized that the ability to build reliable, miniaturized electronic circuits had implications for many technologies, including communications equipment, computing devices, control systems, and numerous other applications. The Americans appeared to have mastered miniaturization techniques that would provide advantages across multiple technology domains, not just in weapons. This suggested that even if Germany somehow survived the war, it would face post-war technological disadvantages that would take decades to overcome. The cost-effectiveness of proximity fuses, despite their sophistication, revealed American manufacturing efficiency that German scientists found remarkable. Intelligence estimates suggested that American proximity fuses cost approximately $20 each to manufacture, expensive compared to mechanical time fuses that cost perhaps $1 or $2, but still cheap enough to use freely as expendable ammunition. Wagner calculated that if proximity fuses improved hit probability by a factor of 5 to 10, then they were actually more cost-effective than mechanical fuses, despite being 10 times more expensive. because they reduced the number of shells needed to achieve any given result. This cost-benefit calculation explained why the Americans were willing to manufacture millions of proximity fuses. They represented efficient use of resources that improved combat effectiveness per dollar spent. German attempts to reverse-engineer proximity fuses and build operational copies were attempted at several facilities but failed quickly. The specialized components simply could not be manufactured with available resources and capabilities. The miniature vacuum tubes required glassworking techniques and quality control that exceeded German capabilities. The miniaturized resistors, capacitors, and other components needed manufacturing processes that were unavailable. Even basic materials like the high-quality aluminum used for fuse bodies were increasingly scarce as Allied bombing destroyed Germany's refining capacity. The reverse engineering attempts confirmed what the initial examinations had suggested. Germany could understand how proximity fuses worked, but could not replicate them under wartime conditions. The post-war period brought additional revelations about proximity fuse development and deployment that confirmed German assessments of their significance. American sources revealed that over 22 million proximity fuses were manufactured during the war, an astonishing production volume that validated German estimates about American industrial capacity. The fuses had been used extensively in anti-aircraft roles, dramatically improving the effectiveness of naval and ground-based air defenses. They had been used in ground artillery roles where their airburst capability had inflicted casualties on German forces that far exceeded what traditional artillery could have achieved. Post-war analysis by military historians concluded that proximity fuses had significantly shortened the war by improving Allied combat effectiveness across multiple domains. Dr. Wagner survived the war and was extensively interviewed by American intelligence teams about German weapons programs and assessments of Allied technology. He spoke candidly about his examination of captured proximity fuses and how it had forced him to reconsider German technological capabilities compared to American achievements. Wagner stated that the proximity fuse represented the most sophisticated piece of military electronics he had examined during the war, exceeding even advanced radar systems in the complexity of miniaturization and rugged design required. He acknowledged that Germany had never approached similar capabilities and could not have done so without fundamental advances in manufacturing technology, materials science, and organizational methods for managing complex development programs. Wagner noted that the proximity fuse exemplified differences between German and American approaches to weapons development. German programs often pursued technological excellence in individual components or systems without adequate attention to manufacturing feasibility or cost-effectiveness. Germany had developed numerous sophisticated weapons that were too expensive or difficult to manufacture in meaningful quantities. American programs, by contrast, emphasized integration of good enough technology that could be manufactured reliably in quantity at reasonable cost. The proximity fuse was not the most sophisticated radio device possible. It used relatively simple superheterodyne receiver technology and operated at frequencies that were not particularly advanced. But it was manufacturable in quantity, reliable under combat conditions, and effective enough to provide significant tactical advantages. This pragmatic approach to weapons development had served the Americans far better than German pursuit of theoretical perfection that often never translated into operational capability. The proximity fuse story illustrated broader patterns in the technological competition between Germany and the Allied powers. Germany entered the war with technological advantages in several domains and maintained excellence in theoretical science throughout the war. German scientists and engineers were as capable as any in the world at understanding fundamental principles and conceiving advanced technologies. But Germany increasingly lacked the industrial capacity, material resources, organized development processes, and manufacturing expertise necessary to translate theoretical knowledge into operational weapons in quantity. The Allies, particularly the United States, excelled at the systematic organization of research and development, the translation of prototypes into production designs, the establishment of manufacturing processes that could produce complex equipment reliably in quantity, and the logistics to deliver equipment to combat forces globally. These organizational and industrial capabilities ultimately proved more decisive than theoretical brilliance or individual technical achievements. The 140-foot kill zone created by proximity fuse shells became symbolic of American technological dominance in the same way that other specific capabilities like the Norden bomb sight or the cavity magnetron radar represented American strengths. These were not just individual technologies but products of comprehensive systems that integrated research, development, manufacturing, and deployment effectively. German scientists examining captured American equipment could understand the technologies intellectually but could not replicate the systems that produced them. This distinction between understanding technology and actually implementing it at scale became a recurring theme in German assessments of Allied capabilities. The psychological dimension of facing weapons like proximity fuses affected German military morale in subtle but significant ways. Soldiers and pilots who understood they faced sophisticated weapons against which they had no effective defense or countermeasure experienced stress and reduced confidence that affected combat performance. The knowledge that enemy artillery shells would automatically detonate at optimal height above one's position made taking cover seem futile and contributed to fatalism that reduced fighting effectiveness. Similarly, pilots facing anti-aircraft fire that didn't require precise aim or timing understood their survival odds were deteriorating and became more cautious in ways that reduced offensive capability. The proximity fuse thus had psychological effects that extended beyond its direct lethality. German soldiers and officers who encountered proximity-fused artillery fire during the Battle of the Bulge and subsequent operations consistently described it as among the most terrifying weapons they faced. The airburst capability meant that shells exploded overhead without warning, raining shrapnel downward into any position. Traditional artillery allowed soldiers to take cover when they heard shells incoming, dropping into foxholes or trenches that provided protection against ground bursts and fragments. Proximity-fused airbursts made such protection useless, as fragments came from above rather than horizontally. German casualties from American artillery increased substantially once proximity fuses were deployed, contributing to the rapid collapse of German offensive capability in the Ardennes and accelerating Germany's final defeat. One of the most remarkable aspects of the proximity fuse story was the security that surrounded its development and deployment. The Americans recognized that if Germany understood how the fuses worked, countermeasures might be developed, or German scientists might attempt to replicate the technology. Therefore, proximity fuses were initially restricted to over-water use where duds would sink and be unrecoverable rather than falling into enemy hands. Only later in the war, when American military leaders concluded that Germany could not effectively respond, even if they captured fuses where they cleared for use over land. This security discipline demonstrated sophisticated thinking about technology security and understanding that technological advantages required protection through operational security as well as classification of technical details. The German examination of captured proximity fuses occurred too late to affect the war's outcome, but provided valuable lessons for post-war military technology development. The recognition that miniaturized, rugged electronics provided decisive advantages influenced post-war research programs in multiple nations, including Germany. The techniques for building electronics that could survive high G acceleration found applications in guided missiles, artillery-fired projectiles, and eventually in space systems where similar ruggedness was required. The integration of radio technology into expendable munitions pioneered by the proximity fuse led directly to development of guided weapons that use radio or radar guidance. Many modern weapon systems can trace their conceptual lineage to the VT proximity fuse and the techniques it pioneered. The story of what German engineers found when they examined captured VT fuses reveals multiple levels of technological competition and industrial capability that determined World War II's outcome. At the most obvious level, it demonstrates that specific technologies like proximity fuses provided significant tactical advantages that improved combat effectiveness. At a deeper level, it illustrates that developing such technologies required not just scientific understanding but sophisticated industrial capacity, manufacturing excellence, and systematic organization of complex development programs. At the deepest level, it shows that military power in industrial warfare depends fundamentally on economic strength, organizational effectiveness, and the ability to mobilize resources for systematic technological development at scale. The 140-foot kill zone that proximity fuse shells created became a concrete measure of American technological sophistication and industrial might. Those 140 feet represented the difference between weapons that required precise calculation and timing versus weapons that worked automatically through sophisticated electronics. They represented the difference between nations with industrial capacity to manufacture millions of complex devices versus nations struggling to produce sufficient quantities of basic equipment. They represented the difference between systematic approaches to weapons development versus ad hoc programs that pursued multiple concepts without sufficient resources for any. Most fundamentally, those 140 feet represented the technological gap that had opened between the Allies and Germany by 1944. A gap that no amount of tactical brilliance or individual courage could bridge. Dr. Wagner and the other German scientists who examined proximity fuses understood all of this at an intellectual level, though accepting it emotionally was far more difficult. They had devoted their careers to German weapons development and had achieved remarkable successes in areas like rocket technology, jet propulsion, and advanced aerodynamics. But examining the VT fuse forced them to confront the reality that German technological leadership had been surpassed, that American organizational and industrial advantages had proven more decisive than German theoretical brilliance, and that the gap would only widen in the post-war period as America's economic advantages enabled sustained investment in research and development that war-devastated Germany could not match for decades. As we conclude this comprehensive examination of what German engineers discovered when they examined captured VT proximity fuses and admitted that 140-foot airburst kill zones ruled the battlefield, several themes emerge with particular clarity. First, technological sophistication in weapons development requires not just understanding principles but mastering the manufacturing, materials, and miniaturization techniques necessary to implement those principles in operational hardware. Second, the integration of multiple technical disciplines into coherent weapon systems requires organizational capabilities and systematic development processes that are as important as any individual technology. Third, industrial capacity and economic strength enable sustained technological development that provides cumulative advantages over time, advantages that cannot be overcome through isolated achievements or theoretical brilliance. Finally, facing weapons against which you have no effective counter or which you cannot replicate despite understanding their principles creates psychological effects that extend beyond direct combat losses. The VT proximity fuse earned recognition as one of the most significant weapons developments of World War II, second in importance only to the atomic bomb according to some assessments. German scientists who examined captured fuses understood this significance and recognized the technological achievement they represented. The 140-foot kill zone was not just a measure of lethal radius, but a symbol of American technological and industrial dominance that Germany could not match. That recognition came too late to change anything about the war's outcome, but provided sobering lessons about the nature of modern warfare and the relationship between technological capability and military power. Thank you for watching this detailed exploration of one of World War II's most significant yet often overlooked technological developments. If you found this comprehensive examination of the VT proximity fuse and its impact on the war valuable and enlightening, please subscribe to our channel for more in-depth documentaries that reveal the hidden technological battles that shaped history. Share this video with others who appreciate military history that goes beyond battlefield narratives to examine the scientific, industrial, and organizational factors that determined outcomes. Leave your thoughts and reflections in the comments below, as we value our community's engagement with these complex stories that illuminate how technological competition and industrial capacity shape military power. Your support enables us to continue producing these detailed investigations into military technology and its profound impact on human history. Until next time, this is the story of how captured technology revealed the vast gulf between theoretical understanding and practical implementation, and how 140-foot airburst kill zones came to symbolize American technological dominance that Germany's finest scientists could recognize but could not replicate. Tentor novamente.